Great. So thanks for the intro, and thanks also for the invitation. And I hope that now that I've moved to Canada, I'll be seeing all of you a lot more. And certainly, I hope that goes both ways. So if any of you are interested in visiting McGill anytime soon, just drop me an email. It's super easy for us to arrange talks and so on and so forth. Okay, so today I'm going to talk about machine learning and 21cm cosmology. And so with 21cm cosmology being a bit of a new field, I think it's incumbent upon us to consider all the different possible ways that we might do data analyses in this new subfield of cosmology, and machine learning, I think, is one of them. But let's step back a little bit and talk about the vision, the big picture here. What sort of context am I thinking of when I'm talking about machine learning? So here's a picture of our Hubble volume, right? This is us in the middle looking radially outwards at our universe, trying to map out more and more of it. There's a natural boundary to it, of course, because stuff way out here, too far away for light to have reached us since the Big Bang. And so we've got this finite volume that we are just trying to map out in more and more detail and to cover more and more of it. So what I've shown here in color to scale is what we've mapped out so far. We've got the cosmic microwave background, the high redshifts, right? Redshift 1100, 400,000 years after the Big Bang. And we also have galaxy surveys and quasar surveys surveying the nearby universe, low redshifts, and the more local measurements. And of course, we have individual, very interesting astrophysical objects here and there. But as far as a systematic mapping of our universe goes, we've got a lot of work to do, especially when you consider a lot of the high redshifts are still very poorly mapped. And also, not only that, we're missing parts of the cosmic timeline, but also that also means a lot of volume, since the Jacobian factor means that volume way out here counts for a lot more. Now, those of us in 21cm cosmology would like to put our bets on hydrogen, right? Hydrogen is everywhere in our universe, most abundant element. So if we have a way of tracing hydrogen, of course, we have a way of mapping out our cosmos. And of course, quantum mechanics tells us that there is such a way to map out hydrogen. You've got the hyperfine spin flip transition, where neutral hydrogen can absorb or emit radio waves and undergo this spin flip. So to trace out our universe, we look for absorption or emission of 21cm photons. And the fact that the rest wavelength is known to be 21 centimeters to very high precision means that this also allows us to look at the observed wavelength, observed frequency, and get the redshift. So we automatically have a 3D way of mapping our universe where the redshift direction gives us a line of sight direction. Okay. So this in orange here is what is potentially reachable by 21cm cosmology. And we're not going to get here this year. We're not going to get here next year. But this is sort of the eventual picture that we hope to be able to achieve at some point in the future. For now, experiments like CHIME, HERA, and all the other sorts of experiments trying to do high redshift 21cm mapping are just targeting a tiny sliver of this. But even so, there's a lot of information just with the current generation of instruments. So to provide some context here, we can think about an experiment like Planck, right? Cosmic microwave background experiment, super impact on cosmology so far. And if we ignore polarization, you can think of most of Planck as having given us these 9 maps, right? Maps at 9 different frequencies, order a few arc minutes resolution, and all of the temperature fluctuation science basically comes out of having measured these maps. Now, even with current instruments, we're already dealing with a lot more data than something like this, right? And of course, this is not to minimize all the really hard, detailed work it takes to go from raw time order data in Planck all the way to these maps, plus all the data, all the work that needs to be put in to go from these maps to science constraints. But with our current generation 21 centimeter cosmology experiments, you are talking about order the same angular resolution, but now with, depending on the instrument, till the 2000 frequencies. Okay, so this is a lot of information. These different frequencies are absolutely crucial because of the spectral nature of 21 centimeter cosmology, right? Each one probing a different redshift. And so this is a lot more data, right? And not only is it really a factor of 2,000 or so, it's actually even harder than that because in cosmology, of course, we care about correlations, right? Not only do we care about the value of this pixel at this frequency, we care about how this value at this pixel at this frequency correlates with every other pixel at every other frequency. So the question then becomes, how do we take advantage of all this information? Right? We've taken these rich data sets, and if we can't extract science from them, then it's kind of useless. Right? So what we'd like to do is take this enormous amount of data and place constraints on theoretical models, and that can come in various forms. We might try to rule out certain theoretical models, say data is inconsistent with that. We might have a fairly flexible theoretical model with a whole bunch of adjustable parameters that we can then put constraints on and say that these parameters have to be within this range or cannot be within this range and so on. And traditionally, with cosmology, you might compute something like a power spectrum, right? That's an intermediate step that you can compute from the data, and you can also compute from theory models, get a bit of a theory prediction that you can then compare to the observations to see what's right. And to go into a little bit more detail here, sorts of things I think about are associated with cosmic dawn and reionization, when the first stars and galaxies were forming. And what you're seeing here is an example, hopefully not too futuristic data cube, of reionization in the 21 centimeter line. So what happens during reionization is that you've got these first generation galaxies giving off lots and lots of UV photons, right? Continual star formation and so on. These UV photons can go out into the IGM and ionize hydrogen there, right? That's what these white bubbles are. These are ionized regions in the IGM where because you're now ionized, there's no more neutral hydrogen and therefore no more 21 centimeter signal for you to see. And as you can imagine, by studying these bubbles and also these non-bubbles, right? You see these dark red regions of higher density hydrogen and light red with lower density hydrogen, therefore a weaker signal. By studying all these patterns, these spatial fluctuations, you can start to learn about the galaxies, as well as any other sort of IGM physics that's going on at this epoch. So this is unwieldy. So you do a data compression step, form something like a power spectrum, right, where you're basically quantifying the power, the variance of these fluctuations on various length scales, right? How much of this pattern here is due to high Ks, fine spatial features, versus low Ks, broad spatial features. We would also like in 21 centimeter cosmology to do this as a function of time, right? Because reionization is this gradual process. Here's a movie done by Marcelo Alvarez, which many of you here know, right? Used to be here at CITA, where you're seeing these ionized bubbles grow larger and larger and larger as the universe continues to be reionized by these first galaxies. Eventually, all these bubbles overlapping, filling the whole volume, and we've taken our universe from being almost all neutral to being almost all ionized, and we say that reionization is complete. So we can look for these sorts of signatures with the power spectrum if we measure it at different redshifts, right? So here I'm showing some example 21 centimeter power spectra going from redshift 11, 10 to 9, and going from black to red to blue. You see the most salient feature is that there seems to be some kind of transfer of power from these really fine scales, high K, high wave number, to large scales, low k. And we can understand this by looking at pictures, right? As reionization proceeds, very quickly, you look at something visually like this, and you say that the spatial patterns here are just dominated by these bubbles. This kind of on-off, this strong on-off pattern that you see. As these bubbles grow, the sort of characteristic length scale of these bubbles grow. And so you get more and more of this power at low k's. Right? It's a bit of a simplified picture, but roughly speaking, that's the intuition here. So clearly, by studying, say, the power spectrum as a function of redshift and scale, we can hope to learn a lot about the astrophysics that's going on here. But what we should also ask is there a way to go from this enormous amounts of data, bypassing the power spectrum, and using machine learning, say, to learn about some of these theory models? Okay? Now, so that everyone's on the same page, I want to also, before I launch into machine learning, just say what I think machine learning is. Okay? Real computer scientists might disagree with me, but this is how I think about it. So the first point they'll probably agree with me on, which is that it's not mysterious magic, okay, despite how it's often portrayed by news articles. Right? It's not some sort of crazy thing that can result in magical constraints that give us information that shouldn't be there. Okay? That's not what it is. So I think of machine learning as learning by example. All right? So as an example of learning by example, here is a classical machine learning problem where you have a whole bunch of images here of different everyday objects. You have planes, you have cars, you have birds, cats, frogs, dogs, and so on. And you might be interested in training a classifier where I give you a new image and it tells you what sort of object this is. Okay? So what machine learning does is it takes a bunch of training images and training labels, and it learns, its algorithm learns a way to associate various features in these training images to these training labels. And then what you can do is take some test data, check that it works with data that you didn't train with, and then also just apply real data to it. And so the way this works is that machine learning is really just a way to do curve fitting. Right? It's a way to fit very high dimensional functions that really mimic physical models. So the way you can think about this is I've got a whole bunch of labels here. Let me just convert these into numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then these pictures I can also think of as numbers. Right? Each picture, every pixel has an RGB value. And I've got a whole bunch of pixels. So I can just flatten the vector here. And so each picture here is represented by a vector. And what we are trying to do with machine learning is to come up with a good guess for this function here, mapping this data to these labels. All right? And so it is just a way to fit higher dimensional data in a way that's fairly powerful and robust and can capture a lot of complexity in our applications. So today I'm going to talk about 3 different explorations we've done in the context of machine learning and 21cm cosmology. This is my take-home message. A lot of these explorations are very interesting. It's probably premature to say that machine learning is ready for prime time in 21cm cosmology, to say that this will just replace everything and do all data analyses for us and it'll be fantastic. We're not there yet. But there are a lot of interesting possibilities out there that I think are definitely worth exploring. So some continued investment, I think, is great for this. OK, so the first project I'll talk about is this idea of speeding up power spectrum simulations with machine learning. And for this portion, when I say machine learning, I really mean the rawest definition I just gave you, where we're basically doing curve fitting. Okay? And the idea is the following. So we're saying we're going to try to measure the power spectrum over a bunch of redshifts. And here you see a lot of these in more detail. And the simulations, the models that go into this, depend on a whole bunch of parameters. Okay, and here what you're seeing is me wiggling a bunch of these parameters back and forth, and you can see the corresponding changes in the various power spectrum curves. Okay, put another way, this is to convince you that if we measure these, then we can have some handle on the values of these parameters. Okay, now there are a lot of parameters here. Right? And we need all of these parameters. There are some that are governing the astrophysics of cosmic dawn and reionization, things like the UV ionizing efficiency, right? How many UV photons are being created by these first galaxies. Some of these are cosmological parameters, telling us things about matter density and the Hubble expansion and so on. And it's important to include all of these. So for instance, here is a forecast for Hera, the hydrogen epoch of reionization array, which I'll talk more about on Wednesday if you're going to the Astro Colloquium. And so what was thought initially was that with the first generation of 21 centimeter detections, that if all you cared about astrophysics, if all that you cared about was astrophysics, you don't need to worry about cosmological parameters in your model. But what we showed was that really no, even at this sort of first generation level sensitivity, whether you fix your cosmological parameters in these error ellipse forecasts for Hera, whether you fix them and you say I just know my cosmological parameters, or you say I'm going to vary them at the level of our current state of knowledge, which is actually very good, right, from Planck and galaxy surveys and so on, it actually makes a difference. Ends up being about a factor of 2. Okay? So we do have to have these models with a lot of parameters. And the question then becomes, how do we adequately explore the parameter space when there are so many parameters? Now in terms of actually fitting the models, this is a solved problem in cosmology, right? We all do this, right? The sort of usual Bayesian thing, say, I want the probability distribution of my parameters given the data that I've taken. It's proportional to the likelihood of the data given the parameters and then my prior on the various parameters. And of course, your instrument, the details about your observations enters at the likelihood, where, for instance, you might write down a Gaussian likelihood, where it's a Gaussian in the deviation between your data and the theoretical prediction for your observables given the parameters, and the error covariance here tells you how noisy your instrument was, for instance. And we can do the usual thing that we do when fitting parameters, basically do an MCMC analysis, kind of walk through parameter space in the MCMC-ish way that ends up giving us a way to just histogram up these results and get confidence regions. Okay? Now, let's not forget that as we're walking through the parameter space here, right, these are different parameters in the model, each one of these points corresponds to another evaluation of a model. So it's a different scenario of our universe. Right? And so what that assumes is that I am able to evaluate these models fairly quickly, which is not always a given. Right? For instance, with the 21 centimeter power spectrum, a lot of these models take, say, order a day to evaluate. And so for every set of parameters you pick, if it takes a day, right, but typical MCMC, maybe you're using 10 to the 4 of these points, that's still a long time. So we set out to try to do something about this problem. And the idea is, as I said, almost quite literally curve fitting to try to emulate this theoretical model. Okay? Where rather than sticking the exact theory prediction that you had from your favorite model into the likelihood, we're going to approximate it. And the way you can do that is to first lay down, to evaluate the model exactly at a bunch of points in parameter space, pre-compute that, and then if I need the prediction at any other point in parameter space, I'm basically doing an interpolation. right? And the idea is that whatever interpolation function you're using here is more efficient to evaluate than a full simulation of some sort, whether it's semi-analytic or a full numerical rad hydro sim or whatever. So again, you have cosmological parameters, astrophysical parameters, and what we wanted to do was to say, run one of these simulations at each of these points, predict power spectra as a function of k and z, as well as other quantities like the neutral fraction as a function of z, how the universe went from 1, all neutral, to 0, all ionized, and then to try to interpolate some of these quantities so that we can evaluate them no matter what model parameters we pick. Okay? So this was work done that was led by a graduate student at Berkeley working with me, Nick Kern. And so that package is available. If you look up our paper, there's a URL there that you can go download the package if you want. But it took some, tricks to get this to work. So for instance, you still don't escape the fact that we were dealing with a very high dimensional space, all right? So earlier I said, at least, it's going to take at least 11 parameters, maybe more, all right? And if I have an 11-dimensional space that I'm exploring, even if I sample, if I lay out my training sets very coarsely, right? So imagine 10 notches along each axis. That's already 10 to the 11 training points. And if each one took a second, forget a day, if each one took a second, that's already 3,000 years. So the first thing you have to ask when you're building an emulator like this is, how do you actually do this efficiently? And the first thing to do is literally to cut some corners, okay? I drew a rectangular training region earlier. But if you look at typical parameter constraints, because of the way typical likelihood functions work, you're probably looking at something more like this, right? Some more slightly elliptical things. And because we're in such a higher dimensional space, if you just cut out the corners, you save on a lot of volume, right? The Jacobian factor means that for a higher dimensional rectangle, the corners are where most of the meat resides, right? Where most of the volume resides. The first thing we do is just cut down dramatically on how much parameter space we have to cover. Once you've defined this, you have to decide, well, how am I going to plonk down my training points? Okay? So one method would just be to plonk them down randomly. Okay? A more efficient way, which is very common in the emulator literature, is to solve the Rook's problem. So if you play chess, you probably know that a rook can only threaten what's in its same column and same row. And the Rook's problem is to say, let me just put down 8 rooks on the chessboard such that none of them can threaten each other. And you can either kind of do this randomly, initialize this randomly, that works fairly well, or you can explicitly build in some sort of maximization thing where you're trying to maximize the resulting distances between them. Right, exactly. That's why that would be one solution to that. But then you wouldn't be kind of maximizing the distance between the resulting distances, right? So you do want to introduce some randomness, because if I did that, then you can imagine that my training samples are going to be very correlated in a sense, right? I'm just cutting through a diagonal in parameter space. That's right. So in practice, you do want to either randomize a little bit or build in that cost function where you're not letting them do that. Now, doing something like this, though, so now thinking about these guys, this as parameter space and these guys as training samples, this is nice because if you look at how it projects down to a lower dimensional space, you get a fairly nice coverage in any sort of lower dimensional projection, which is good. We want to be able to cover our different axes fairly well. Now, once you've laid down everything here, you have to ask yourself what, we're going to interpolate between them, but what are we going to interpolate? So, for instance, each one of these points gives you a different prediction for, say, the power spectrum, and as well as things like the ionization fraction and so on and so forth, or whatever other parameters your simulations give that you want to know about. So one thing to do is you could just say, okay, each point has a data vector here, and I'm just going to, if I have n elements in this data vector, I just write down n interpolation functions, right? I take each of these elements and I come up with an interpolation function. So that turns out to be fairly wasteful, because if you look at a typical quantity that I'm trying to emulate, they don't vary in arbitrary ways, right? So in other words, the different elements of this vector aren't really that independent. So take the neutral fraction curve as an example, right? We pretty much know it goes somehow from 1 to 0, and depending on what knobs you're twisting in the theory model, it might do so in a different way. Maybe it won't, maybe it'll go through here or something. But there are constraints on the possible variations here. So a much more economical way to do this is basically to do a principal component analysis, take a bunch of the typical data vectors that you're predicting, and just forming the covariance of them, and asking in what principal ways, what are the most dominant ways in which these curves can vary over my parameter space. So in doing so, for instance, you can come up with an eigenbasis that very compactly, with just a few eigenmodes, really capture all of the likely variations you're going to see in parameter space. So now you're kind of, instead of interpolating, say, 100 different quantities, the answer might be 3. Okay? And having established that, how do you actually do the fit? Some of the earlier emulator literature just used kind of the most obvious thing you might think of, which is a higher order polynomial. That kind of works. Basically works if you go to high enough order, especially. Here are some example training samples. We can do a polynomial fit to these, and of course, where you trained, you expect to do quite well. And of course, where you didn't train, results aren't so great. Right? Here in pink are cross-validation samples, where these are example similar simulations that we did, that we kept aside and didn't use as training samples. We use this to kind of check our work, essentially. Now, another possibility is to do a Gaussian process fit. Okay? And with the Gaussian process, basically you're saying that for this continuous curve, you're going to model every point on this curve as being drawn from an infinite dimensional Gaussian. Okay? And if you have a bunch of data points and you do a Gaussian process fit, colloquially, sometimes people say it kind of just looks like you just picked up a pencil and just drew a reasonable freehand smooth curve through it. Okay? And this also comes with a lot of technology to come up with predictions on the errors of the resulting fit. So this is nice. What we did was that we used the Gaussian process to do this sort of fitting. And one of the features here, if you model your input covariance well, is that it knows when it's extrapolating. Okay? Obviously, things are a lot safer when we're interpolating rather than extrapolating. And the errors kind of know to blow up there, which is great. That's what you want. And the cross-validation suggests to us that we're able to get fairly good errors with this approach, kind of order a few % errors across most of the parameters, not parameter space, over most k's and redshifts. And of course, with something like this, you can always improve the performance of your emulator just by using more training samples. Now, going beyond just saying that our errors are relatively low, though, we can also incorporate some of these errors into our analysis as well. So if this is our likelihood, and we know that we are not quite using the exact model in our fits, but instead had some kind of emulation error, we can put this in. And basically, if we understand our statistics of this emulation error, which we can do through a combination of the the covariance statistics outputted by the Gaussian process, or we can kind of do it empirically a little bit with our cross-validation. If we understand those statistics, we can marginalize over these delta f's, the deviations of these models, basically integrate over all of this, and you can show that this can be written as effectively having increased the error bars on your measurement. And so in some sense then what you're doing is you're really being a true Bayesian here, right? Like your error bars partly contributed by the error bars in your observations, but also partly due to your lack of knowledge of your true theoretical model. And doing things like this is nice because what you want to be really worried about is what happens when you have a situation like the one I alluded to earlier, where you have a training point here, not a training point. The reds are the training points, but you take your data and your best fit happens to be right near your training region, right? So people have gotten into trouble in the past before where there was an artificial cutoff beyond here and resulting in constraints that contours that kind of artificially cut off beyond this place and gave you overly optimistic confidence regions. But what we have in our code is the emulator, again, knowing that it's not so great towards the edge of the training regions. And so these contours always kind of, if this blue point is near the edge, it kind of knows to creep out there to let you know that it's not really saying much out of this training region. And this was nice, putting all of this together. It was nice because it pushed the state of the art back a few years ago from being able to do these sort of 3 to 5 parameter fits for forecasting and eventually for data analysis for 21 centimeter experiments, going from 3 to 5-ish parameters to doing 11-dimensional parameter spaces, or potentially even more if you want to train a more complicated model. Now including both astrophysics as well as some cosmological parameters. Okay. All right, so that's an example of something where you're using these ideas of curve fitting to help your power spectrum analysis. Okay. What I'd like to talk about now is whether you can bypass something like the power spectrum entirely and go directly from the maps of the 21 centimeter emission down to constraints on theoretical models. Yeah?
Quick question about this
big
triangle plot
yeah.
Before. It looked like some of the cosmological parameters have degeneracies, which we know, and it looked like a lot of the astrophysical parameters do not have degeneracies. Are those parameters chosen such that they don't have degeneracies, or like, is there a special reason why these things are degenerate?
Yeah. Basically, I'll give you the true but embarrassing answer, which is that the code we used, it was easier to pick the cosmological parameters they picked, right? So in other words, in some sense, it's kind of strange to, for example, be varying little h, omega m, and sigma 8 like that, right? There's a reason, for example, that with Planck, you do things like, you theta is one of your parameters rather than little h, right? And so it was for convenience, and so that's why some of those degeneracies look a little bit funny, but there were no conscious choices on our part to intentionally pick, things that were not degenerate. All right, so what we would like to know is whether machine learning can help us here. Bypass the power spectrum, go straight from these maps all the way to constraints on the theoretical models. This is a really interesting avenue to go down because what we would like to do is to go beyond the power spectrum. Partly, this is motivated by how we make our measurements. So remember that we're trying to make these 3D maps. We've got 2 angles on the sky, right? That's represented by one axis here, this vertical axis. And then we've got the redshift direction, right, which has 2 purposes. One is just that it's our line of sight direction. The other, though, is that it really is a redshift, right? It really encapsulates our cosmological evolution. So you have this funny business here where these big data boxes that we're measuring, the back end of the data box corresponds to a universe that's younger than the front side of our data box, right? Which means that the statistics here is non-stationary. Right? And really, in principle, if your statistics aren't stationary, you have no business working at power spectra. Well, you can, but it's, there's more information there. Currently, with our current experiments, this is probably completely justified given the fact that we haven't even made a detection yet. We just chunk up our data volume, right? So we say, I'm going to draw these white regions, and for each one, I'm going to say approximately the cosmological evolution is fairly negligible, and I'm going to form a power spectrum per redshift like this. That's why I wrote P of k, comma z. Right? But this is a really inelegant solution to the fact that we are measuring a light cone. Okay? And what we would like to do, ideally, is to have something that allows us to process an entire thing like this. Moreover, if we're just working at power spectra, we don't capture non-Gaussian information, right? If you take a field and you histogram it up and it's Gaussian, then we know with Gaussians that if you know the mean and the variance, you figured out everything there is to know about the field. Right? You take something like this, histogram up the voxels, you are definitely getting something highly non-Gaussian. And so that's kind of annoying if you want to write down simple statistical things, but also an opportunity because it means that just measuring the power spectrum, right, which is a variance, a Fourier space variance of power, you're not capturing everything. So in principle, direct constraints using images could help us extract more information. So what we sought to do was to kind of borrow from the success of the computer vision community, right, with convolutional neural networks, CNNs. So for those of you who aren't familiar with this, I'll walk through this a little bit. You've basically got this super complicated machinery where you take in images and you go through a whole bunch of these layers. And there are different types of layers. There's convolutions, there's subsampling, and there's fully connected layers. I can stack them in all sorts of creative ways with different sizes and so on. And so to start off with one of the convolution layers, it's exactly as the name suggests. Okay? You are literally doing convolutions, the same way we normally think about them. Right? You've got a convolution kernel of some sort, right? Sliding it over the image like you normally do with a convolution, and you get a convolved image, here green in this picture, pink over here. And what you're doing is that you are intentionally picking these weights in these convolutional kernels to try to pick out important features that are important for your science. Okay? I haven't told you yet how I'm going to do that, but I will in a second. So you have a convolutional layer, typically first. Okay? And then you might go to subsampling, which in the computer science lingo is pooling. So that's literally just trying to reduce your data volume. So you might want to go from a 4x4 grid to a 2x2 grid of data. Max pooling is very popular in the computer science literature, where you literally take the maximum value in each of these sub-boxes and just put it here. In the kind of cosmology cross machine learning literature, average pooling has also found its place and has been very useful, better than max pooling in some applications, where you, as the name suggests, you average to get everything in these sub-boxes. So you can do this multiple times. Very often you do a convolution, a subsampling convolution, downsample, and so on and so forth. And then usually what happens towards the end is that you have what we call fully connected layers, where you've got this input data coming out here, and then all you do is that you're taking weighted linear combinations of these data, and ideally what pops out are the things that you want to learn. Okay, so in this case, it might be astrophysical and cosmological parameters. And again, you've got these variable weights that you're going to adjust to try to get these reproduced the best you possibly can. Okay? Now, there's one big omission in what I just said, which is absolutely crucial to all of this working, which is that after each of these layers, you have to put your data through some sort of nonlinear function. Okay? In principle, any nonlinear function will work. In practice, things like this rarely rectified linear unit, for example, is a popular choice. You basically take every single pixel in these images and you just put it through this nonlinear function. And that's really important because if I omitted these nonlinear steps, every single step I have shown you up till now is a linear operation. It's representable by a matrix. So all I would have done without these guys down here is go put our images through a whole bunch of matrix multiplications. And multiplying n matrices together is basically the same as, it's equivalent to multiplying by one big matrix, right? So if we didn't do this, all that this would be capable of doing would be to fit linear models to our data. And we know the truth is typically more complicated than linear, right? With these sort of nonlinear steps interleaved here between these different steps, one can show that this sort of fancy architecture can, in principle, approximate any sort of function out there. Okay? So the idea is we've got this big function representing this thing, put in input images, and out pops the answers we want with some sort of adjustable knobs. And what we do is that we create lots of training images and training answers where we know what these correspond to all of these parameters, and you basically adjust these knobs until you get something that reproduces the training data very, very well. Then you freeze all these weights for your convolutional kernels, for your fully connected layers, and so on. And then after that, you can put in your test images and see if you get good results, or put in real data and get your results. So we tried to do this. This is work done that was led by Nick Gillet at Pisa. So we took some of those light cones that I showed you earlier and basically had this sort of architecture where we did a convolution, a pooling, convolution, pooling, and then 4 fully connected layers that then outputted for us 4 parameters of interest. One which is T virial during reionization, basically a proxy for the mass of these ionizing halos, okay? Basically saying, are we reionizing with more massive galaxies or less massive ones? Their UV ionizing efficiency is another parameter, how many UV photons produced per galaxy. The X-ray luminosity of each of these galaxies, as well as the minimum X-ray, I should have said photon, X-ray photon energy. So the idea here is that for low energy soft X-rays, it's actually relatively easy for the interstellar medium of these galaxies to absorb them before they can get out into the intergalactic medium and have an effect. And so there's some sort of minimum threshold of X-ray photon energy that must be met before you can affect the IGM. So here are some results. What I'm showing here are results from our test data, right? So the data that was not being trained on but set aside for testing. In each case, I'm showing on the horizontal axis the true value that we know. On the vertical axis, we've got the recovered value. Generally, you have fairly reasonable recovery, sort of 1 to 10% level recovery of these parameters. There are some interesting features here. For example, if we look mostly at this plot down here, if you've got good eyes and you can look at see the yellow here, what you notice is that our recovery is less reliable when the UV ionizing efficiency is very high, okay? And the reason for that is that this is basically controlling the rate of reionization, right? If I really yank up the UV ionizing efficiency, I'm producing lots of UV per galaxy, and I can reionize my universe very, very quickly. So what happens then is that these transitions, say from having some ionization to having nothing, happens very, very quickly in this picture. You don't have this extended bubble structure with lots and lots of features for the convolutional neural net to grab onto, right? In the extreme case, you would just go directly from, say, blue to black and have nothing to really latch onto. And so that's why if I yank up the ionizing efficiency, typically my recovery is not quite as good. This plot is also interesting. This was probably the most anomalous one out of the 4, right? Where you notice that if the minimum photon energy of X-rays coming out of these galaxies is very high, I also basically can't, right, I mean, this regime is basically not recovering anything, right? The reasoning here, what's happening is that if I really turn up the E0, basically turn up the typical energy of X-ray photons coming out of these galaxies, high energy X-rays are very hard to absorb, right? The cross section for hydrogen absorbing high energy X-rays goes like 1 over E cubed, okay? So what usually happens with these X-rays is they come out and you need to, it takes some time, they have to travel along and chill for a while before the universe's expansion has redshifted them closer to UV before they can be efficiently absorbed by the hydrogen, okay? What's happening in this sort of regime, where basically we can't do anything, is that your galaxies are producing UV photons that are so high energy that in the entire time of our simulation, there isn't enough time for these photons to redshift into be close enough to UV to be efficiently absorbed. So these photons are basically having no effect on the picture, right? And therefore, if there's no effect on the picture, again, machine learning is not magic. It's not going to give you information that wasn't there. Okay? So one question is, is this ready for prime time? Am I ready tomorrow with, say, Hera images, like plugging them in and getting wonderful parameters? The answer is probably not. This study was a bit of a proof of concept study. We didn't put in realistic instrumental noise or realistic foreground contaminants. And those of you who are familiar with this field know that's basically half the challenge, right? We obviously need to try this with more parameters, right? I argued, yeah.
Since you mentioned more parameters, your parameter list would look like it was able to incorporate the H0 discrepancy between C and D.
Yeah.
I mean, expansion has to be much more complicated if it's really expansion history.
Yeah.
So, more broadly, the question would be, what I said, 21 centimeter constraint.
Sorry, said it, I can't hear you.
I read 21 centimeter constraint. Significant deviations from a symbol down to CDM.
Yeah. So it's actually not very sensitive to that unless you make a lot of assumptions about the astrophysics. The parameter that I would say that we need to include all those parameters to not be biasing ourselves. But in terms of the only parameter in this sort of analysis that we might hope to be able to say something about is sigma 8. Basically, and not because this is this is probing the right scales to directly measure sigma 8 or anything, but basically because if you change sigma 8, you change the growth history, right? And that will in turn change when reionization happens, and it's only through there. But for the other parameters, you are probably not going to get too much except by combining with a whole bunch of other probes. The other thing I think we should do with an analysis like this is, I talked about this as kind of beating power spectrum analysis in the sense that I'm trying to replace power spectrum analysis. But, why can't we just be friends, right? We can always do the power spectrum analysis. And so we should be standing on the shoulders of giants. So one interesting possibility is to take a power spectrum constraint where you, by definition, have said, okay, everything within these ellipses is basically consistent with my power spectrum measurement, and then just training on where within this ellipse I am, so that by construction, you might fail, but by construction, if you succeed, you are getting at, by definition, information that cannot be obtained from the power spectrum analysis alone. Okay? Now, another question we can ask is, rather than taking a fixed model and trying to constrain parameters within the model, can we actually just figure out what models are correct, right? So one question that has been on the back of everyone's minds for a long time is reionization driven by galaxies or AGNs? This question seems to go in and out of style every few years, depending on how confident we are about various things. 21 centimeter, we hope, will tell us something about that, right? With AGNs being more biased, typically larger, fewer bubbles. And so we said, let's train a neural network on this, have some images that are generated from simulations driven by AGNs versus generated from simulations driven by galaxies, and just predict one number at the end of it, 0 or 1, okay? And if it's 1, AGN, 0, galaxies. And so one of the things we wanted to do, changing whether it's reionization by AGNs or galaxies, does change the power spectrum. But the interesting regime is where the power spectra are relatively similar. So what we found with these simulations was that, as a kind of a shortcut because we didn't want to run our simulations again, our AGN power spectra of redshift 8 tended to look a lot like our galaxy power spectra of redshift 7. So we just did a simple first pass study to see if we could distinguish between images in these two sorts of scenarios where we found empirically the power spectrum is relatively similar. It's okay. It's not amazing. Here's a fraction of images that were correctly classified in the testing. For those of you who are 21 centimeter aficionados, you know what I mean when I say the wedge slope, the foreground wedge slope. Those of you who aren't, just imagine 1 is pessimistic foregrounds, 0 is if foregrounds are perfectly removed. And you can see maybe with next generation instruments, kind of is okay. Current generation instruments, if we do a good job with foregrounds, is better than guessing, right? That would be 50-50. If we don't, then it's basically like we're guessing. Yeah.
So you're looking at redshift 7
Yeah.
galaxies versus redshift 8 AGN.
Yes.
But wouldn't the redshift itself give you, I mean...
Right, exactly. So this is a very artificial situation, and what I was about to say is this, I should caveat all of this by saying this was kind of a first pass study, and for example, we did not use timing information in this classification. I expect the timing information will be hugely informative, right? Certainly with the power spectrum constraints, say with Hera, the bulk of the constraining power is coming from the timing information. So lots more work to do. So what else might we do? I think there are a bunch of other opportunities out there. One that I'm excited about was inspired by 2 of my colleagues at McGill, where they were trying to use machine learning to see if they could look for signatures of cosmic strings in cosmic microwave background maps, right, CMB maps. And initially, they just tried a classification kind of thing, like I just mentioned, where you say, I've got some maps that I know I put in some cosmic string signatures and others where I didn't, and I'm just going to predict a 1 or a 0. Were there cosmic strings in there? They found that worked horribly. What worked much better for them was if they trained a network to take one of these maps and to predict a second map that was where each pixel gave you the probability of there being a cosmic string in there, and using that map to then extract, the knowledge of whether you've statistically significantly discovered a cosmic string, right? And they found that worked way better, converged much more quickly, for example, in training. And the reason for that was you were basically coaching the neural network into saying there are some localized map space features that you should be looking for in order to get at this. So I think I'd love to redo the regression problem I mentioned earlier, but as an intermediate product, try to measure the ionization field, which is similar to our probability field, right, is going to be between 0 and 1. And I'm hoping that I can just take all their CNN architectures, put it into my code, and then it will just magically work. So that's one interesting avenue. Another one, which appeared on the archive not too long ago, led by Josh Kerrigan on behalf of the Hera collaboration, was to see if we can use machine learning to flag radio frequency interference. All right? So those of you who look at radio data, probably accustomed to these plots, frequency versus time, waterfall plots. And for example, something like this might be a radio station, right, at a specific frequency and just persisting through time. So we have RFI flaggers right now, but what Josh asked was, can we do it better with neural networks? And basically his answer was sometimes, right? For certain styles of RFI, he found that it worked very well. For other signatures, I haven't shown you an exhaustive assortment here, it didn't work quite as well. But one intriguing possibility is that this is still much quicker than the traditional flagging algorithms. So you can imagine using them in conjunction, right? Like having a quick CNN flag things as a first pass, and then maybe you lessen the burden on the other algorithms. We can also get at, I'm hoping we can get at parameters that aren't nicely constrained by the power spectrum. A few years ago, I gave a seminar here suggesting that maybe we could use 21 centimeter cosmology to come up with constraints on CMB tau. That got some great feedback during that seminar, which was very, very true, which is that what I was saying was extremely model dependent and therefore might not be as robust as we would like. Using machine learning is still quite model dependent, but if we can tune our machine learning parameters such that we know we are intentionally not trying to use the power spectrum information, so that they're basically orthogonal ways of getting at the same answer, you still don't alleviate all those concerns, but at least if you get consistent answers, you might build a little bit of confidence. And finally, I'm very excited about the possibility of generating simulations with machine learning. Some of you might be familiar with these. These are fake people, okay? So these are not real celebrities. What happened here was that these computer scientists took real pictures of real celebrities, fed them into a neural network, and trained the neural network to convert white noise into fake celebrities. And these are the results, okay? Which is kind of uncanny. Can we do the same for these large simulations? And this is important because even with like really great simulations, say several hundred megaparsecs wide, if I'm talking about comparing this to data that I think resides at redshift 20, 400 megaparsecs at redshift 20 is still a tiny, tiny fraction of my field of view, right? So what I'm excited about is using these sorts of techniques to generate really large all-sky simulations, not necessarily because they will be good enough to directly produce science constraints, but because wide field simulations like that would be great for pushing through our pipelines to check for systematics and make sure that we're not doing stupid things in analysis and so on. So, I've talked about a few possibilities, some initial explorations into machine learning in 21 centimeter cosmology. I think you'll agree with my take-home message that it's probably not quite prime time for all of these techniques yet, but there are a lot of interesting possibilities out there, so I think this is definitely worth exploring. Thank you very much.
Here from particle physics on the 8th floor.
Okay.
We are starting to use machine learning in a lot of our particle physics searches now. So, for example, on the model constraints side, we have these minimal supersymmetric standard models with like 100 parameters that we try to reduce to about a dozen parameters, and then take results from Large Hadron Collider and try to use them to constrain those models. And then on the side of classifiers, we have data coming in that we want to decide whether it's a background event or a signal event, or assign it a probability of being signal versus background, which we saw better. So we've been sort of trying to apply machine learning to a lot of these things on the particle physics side. I wonder if you guys are sharing any software with us or are interested in sharing with us.
We are interested, but we are currently not doing it for no good reason other than we haven't gotten that far. But yes, like we would love to.
Okay, so come visit us.
Sure, yeah.
Yeah, so one of the things that we've run into a particular roadblock with in a lot of occasions is overtraining issues.
Yeah.
Have you run into the same kind of thing?
Yeah, I mean, that's basically the whole name of the game, right? Like overfitting and all that, because you're, unlike normal curve fitting, you're basically the adjustable knobs you have in the neural networks far exceeds the number of data points and constraints you're trying to do. And so basically you're essentially massively overfitting something and then walking back just enough so that you're not doing that. So we've definitely done that before. The first time I, for example, ran the regression problem to try to get those astrophysical and cosmological parameters, that gave me like, 0.01% errors. And that was wrong. That basically came down to the fact that in my training images, I wasn't reseeding the initial density field of the universe often enough. So it was basically memorizing exactly where an ionized bubble was going to happen, right? So then it basically kept waiting for it, and it's like, once it's there, all right, great, reionization happened, and I know that this is the timing of reionization. So yes, I've run into that, and I don't have a silver bullet other than, we're usually just careful and really put our emphasis on the cross-validation and all that.
And then when you do your CNNs, there's all kinds of computer science literature on how to design the network in terms of how many layers they should be,
Yeah.
fully connected, and so on and so forth. Actually understanding that when you're not a computer scientist is kind of
Yeah.
so we think that we often get that wrong or haven't optimized it properly.
Right.
Have you found any computer scientists who can?
Yeah. I mean, I basically found a computer scientist who likes to talk to me. Siamak Ravenbach, who's at UBC, and he's great, and he loves science applications. I can send you his email if you want. And he just loves all of this stuff, and I just talk to him and ask him like, is this a good architecture to use? And he'll literally say things like, oh, don't do that, don't do that. Like that was back when people didn't understand blah, blah, blah. And I'll say to him, that paper was from 2 months ago, right? Is your field really moving so quickly that like that is a stupid thing to do at this point? And his answer is yes. But yeah, come up afterwards and I'll give you his email address. He'd love to talk to you.
Yeah, so obviously if we're going to do a nonlinear analysis of maps in general, the old-fashioned way has been to look at some 3-point endpoint functions.
Yeah.
Is that, have you ever compared if that gives you more information, if that gives you more or less information?
Yeah, I mean, I have not. The basic answer is I have not. The endpoint functions are tricky. I'm not. So what that doesn't solve, for example, right, is the light cone problem, right? Because you're still, unless you do extra tricks, right, you compute like a bispectrum, trispectrum, you're still assuming stationary statistics. And so that's part of the reason I'm gravitating towards this. But yes, basically, we have not done a side-by-side comparison to see how much more information we can get. We're not at that stage yet. I mean, if you look at our constraints and our projected constraints from this, we're barely doing as well as the power spectrum analysis, right? So, we probably aren't getting that much more information than the power spectrum, which is partly why I'm starting to get interested in constructions where I'm explicitly not using the power spectrum information to try to do better.
Questions? Okay, if there's nothing further, let's thank Adrian.
All right, thank you.